Our paper's title is Robots with Attitude, Singularity-Free Quaternion-Based Model-Predictive Control for Agile-Legged Robots. All three parameters representations of 3D rotations suffer from singularities. This prevents us from designing controllers for behaviors with large attitude changes. In these two videos, all the angle-based controllers reach the singularities that fail to reach the desired attitude. On the other hand, the singularity-free representation with the fused parameters is the unit quaternion. In this paper, we used it in our MPC controller for legged robots. To derive quaternion differential calculus, we chose to use 3-parameter vectors to represent infinitesimal rotations, because differential rotations are in the 3D Euclidean space. We used the Cayley map to reconstruct the unit quaternions from 3D vectors. Then we can derive the Jacobian and Hessian for functions with unit quaternions variables. We used the following standard discrete time nonlinear MPC problem formulation in our controller. Specifically, we used an LQR-style cost function plus a special term for unit quaternions. The constraints include dynamics constraints with unit quaternions and friction cone constraints. Since the distance between unit quaternions cannot be captured accurately by the two-norm distance, we used a metric that is easy to compute and monotonic with the geodesic distance. We modified Ultra, an open-source augmented Lagrangian iterative LQR solver, to solve the unit quaternion-involved MPC problem. Using the derived quaternion differential calculus, the linearized aerostate dynamics and the second-order Taylor expansion of the action value function are modified. In the first experiment, our controller successfully enables real-world dynamic walking while maintaining full attitude control. We control the robot to walk around in a trotting gait while continuously sending sinusoidal angular velocity commands. We also validated the robustness of our controller by disturbing the robot's torso during trotting. In the second experiment, our approach successfully enabled a unitary goal-one robot to stand between two walls without any additional support. Though we can slightly adjust the pose, the control performance is limited due to motor thermal and power constraints. We also achieved accurate attitude control in simulation with this setup, given sinusoidal angular velocity commands. In the third experiment, we achieved L-borne attitude control for a falling quadruped with roll and pitch reaction wheels. Monte Carlo experiments are performed. Quaternion MPC achieved a 95% success rate, but Euler MPC only achieved 41%. In the fourth experiment, we evaluated our method in simulation on the MIT humanoid. Quaternion MPC effectively balanced the robot during large attitude changes, while Euler MPC suffered from singularities.